Welcome to CCCS122 Discrete Mathematics. This is Chapter 7, Discrete Probability. Everything you've learned so far about counting in Chapter 6, preceding chapter, uh, is going to form the basis for computing probabilities of events, of outcomes that happen in random experiments. So in the following, we'll use the notion of an experiment for a procedure that yields one of a given set of possible outcomes. The outcomes are atomic and they're disjoint, meaning that outcomes do not overlap. This set of possible outcomes is called the sample space of the experiment, and an event is a subset of the sample space. Now, if this seems a little abstract, then I'll try to go through the same things, the same concepts, giving you an example. So, for example, an experiment can be something like the roll of a die. When you roll a die, you have, at the end of the roll, you'll see one of the 6 faces of the die come up on top. Those 6 faces, those 6 different faces, are 6 different possible outcomes. Now, what we do is the outcomes of experiments can sometimes be non-numeric, not numbers. So, for example, the face that has one dot on it is just a shape. It's a geometric shape. There's a face with 2 dots on it. Now, usually when we talk about the faces of a die, we associate numbers with those faces, numbers with those outcomes. And that's what we do as well. And the numbers are usually picked, all the possible numbers associated with outcomes are what make up the sample space. Sometimes we'll also refer to the set of all possible outcomes, meaning those 6 figures that you see on top. Sometimes we'll refer to that as the sample space. But there's definitely a mapping happening here from outcomes to not just numbers, but real numbers. So in this case, the sample space consists of the integers 1, 2, 3, 4, 5, and 6. And you can already see that there's this capital X over here. I'll come to that in a minute. Now, each of these individual outcomes in general, it's oftentimes also denoted by some lowercase letter, like a small x in this case. So X, an outcome, is an element of the sample space usually denoted by a set with the name S, which itself is a subset of the set of real numbers. Now, this mapping that is happening here from outcomes to numbers has a name as well. We call that a random variable. Random variables are usually given given symbols, capital letters. In this case, X. That's why we have these capital X's in the subscript of the sample space. So, random variable X, and I'll come to that later in the chapter again. Random variable X is basically the mapping that specifies that which outcome is mapped to which number on the real number line. And a little more detail. So we have outcomes. Those outcomes are in turn mapped to real numbers. And in this case, each outcome, and I'll be using the number that is mapped, that the random variable maps to each outcome, and the outcome, meaning these pictures that we have up here. I'll sometimes be using these terms interchangeably. Each of these outcomes has a probability, of course. So, and not only that, so each of these columns here represents is specific to one outcome. But on top of outcomes, we can also define events. And events are basically subsets of the sample space or collections of outcomes. So, for example, an example of an event for this particular experiment could be that we roll an even number. So rolling an even number is an example of an event. And in that case, the event even numbers would contain basically these three outcomes that we see: 2 dots, 4 dots, or 6 dots on the face of the die that comes up on top. So outcomes can be corralled, can be put together to define events. Just like that, you could, of course, define an event that an odd number shows up, or that the number is less than or equal to 4. So that would include the outcomes 1, 2, 3, and 4 dots, and so on. You can make up any event that is needed for your problem. Now, each outcome over here has a probability. There are 6 possible outcomes, assuming that the die is fair, is not loaded, is not biased in any way. Each outcome will occur with a certain probability. That probability in this case is 1 by 6. These are the actual probabilities for a fair die, but in general, the probability of each outcome, of each element of the sample space, each value that X can take on, that probability can also be denoted symbolically, and it's usually, so for example, for each outcome, I've given those symbols down here. So P of X of 1, P of X of 2, P of X of 3, P of X of 6. You can see this is actually not just any symbol, it's a function. P of X is a function over here, and it is taking as arguments different values from the sample space, the numbers 1, 2, 3, 4, 5, or 6. So basically, P of X of 1 is equal to 1 by 6. P of X of 2 is equal to also 1 by 6. And in this very simple experiment, the values of the function, of this function, P of X, they're all the same. They're all 1 by 6. Now, since we're talking about a function over here, this function has a special name. This is called a probability mass function, or PMF. And it is denoted like so: P sub X of X, and X, small x over here in the argument. These are the different outcomes, the different elements of the sample space over here. The numbers 1, 2, 3, 4, 5, and 6. Now, a function, we know that usually a function can be plotted, and I'll show you that here. So this is the PMF of a fair die. Possible outcomes 1, 2, 3, 4, 5, and 6 on the x-axis, on the horizontal axis, and on the y-axis, or on the vertical axis, we have the PMF, the probability mass function, of course. And usually this is how we draw probability mass functions. We represent each probability value by this kind of plot. This is called a stem plot. This doesn't look very interesting because the probability of each outcome of the experiment is equal. It's 1 by 6 over here. Now, if all outcomes in the sample space are equally likely, then the following definition of probability applies. The probability of an event E, which is a subset of a finite sample space S of equally likely outcomes, is given by the cardinality of outcomes in E, or the cardinality of the set E, consisting of all outcomes in the event, divided by the cardinality of the sample space. Now, the number of outcomes in the event set will always be less than or equal to, at most equal to, the number of outcomes in the sample space. This guarantees that the range of values for probabilities is anywhere between 0 and 1. 0 means an event that will never happen. 1 is an event that will always happen whenever the experiment is carried out. Okay, so let's get into some examples. So got the first example over here, example 1. A vase contains 4 blue balls and 5 red balls. What is the probability that a ball chosen from the vase is blue? There are 9 possible outcomes, because there are 9 possible balls that you could pick. And the event blue ball is chosen comprises of 4 of those outcomes. For that reason, there are 9 possible outcomes. For that reason, the probability of this event is 4 over 9, or you can express it in, you can write it in decimal form, and so on, or in percentage form, 44.44%. And then we have example 2. What is the probability of winning the lottery six out of 49? What is the probability of picking the correct 6 correct numbers out of 49? Now, it's not as straightforward as you think. So there are 49 possible numbers to pick. You have to pick the 6 right ones. Now, out of all the possibilities, only one will make you win the lottery. Now, we already know how to find this. This is basically a problem in which we do not care about the order of things. We just care that the right, how many different ways we can select 6 items out of 49. How many possible combinations are there? And there's only the event of winning consists of only one right combination. So the hard part is finding all the possible ways of picking 6 out of 49. The answer for that is 1 over C combination 49, 6, which is a very large number, 13,983,816. So just in case you don't remember, this is basically NCR, or in this case, 49C6. Okay. Now, let's let E Let's consider E to be an event in the sample space S. The probability of an event minus E, meaning the complement of E, is given by 1 minus the probability of E. That is the probability of the complement of E. Well, it's pretty much common sense. The probability of something not happening is 1 minus the probability of it happening. This can also easily be shown like this. So what is the number of outcomes in the non-event, not E? It is number of elements in the sample space minus number of elements in E divided by, and to find the probability, divide by the number of elements in the sample space, which you can rearrange to write like this. This, of course, is the very definition of probability of E. It's 1 minus probability of E. Sometimes it is easier to find the probability of an event that you're interested in by finding the probability of the event not happening. And we've seen counting those possibilities. We saw that in the previous chapter in at least one example. Okay, another example here. A sequence of 10 bits is randomly generated. What is the probability that at least one of these bits is 0? So the probability that 1 is 0, or that 2 are 0, or 3 are 0, or 4, 5, or 6, or 7, or 8, or 9, or all 10 are 0. This is one of those cases in which it is convenient to flip the problem around. What is the complementary event to this? The complementary event is where, well, we're trying to find the probability that at least 1 is 0. The opposite of that is where none is 0. And that's pretty straightforward. It's basically the probability that all 10 bits are actually 1. And that probability, that is actually pretty straightforward. There are a total of 2 to the power 10 possible ways this 10-bit string could come up, which means 2 to the power 10 equal to 1024. Only one of them contains no zeros at all, and that's the string that I have underlined over here. And so instead of counting all the other possibilities, it's easier to count the one that we're not interested in, the one that we're trying to exclude. For that reason, the probability of the event not happening in this case is 1, the string, over 1024, meaning size of the sample space. And so then the probability of E is just 1 minus the probability of the complementary event, which is 1 minus 1 over 1024, which is just 1023 over 1024. Okay, what is the probability that at least 2 out of 36 people have the same birthday? So the sample space S contains all possibilities for the birthdays of 36 people. So that is 356 to the power 36. 36 people, 365 possible birthdays in a year. Now let's consider the opposite event. What is the opposite that at least 2 out of 36 people have the same birthday? Meaning 2 can have the same birthday, 3 can have the same birthday, 4, 5, 6, all the way up to 36 having the same birthday. That's a lot of cases. The opposite of that is that no two people out of 36 have the same birthday. So, in this case, the first person can have any birthday you want. So, for the first person, you have 365 possibilities. For the second person, that leaves the second person can have any birthday other than the one the first person had. So, 364 possibilities for the second person. Then 363 possibilities for the guy after that. 362 possibilities for person number 4, and so on. This must seem familiar because this means that the probability of the complementary event can be found like so. And since we're originally interested in P of E, that is simply 1 minus P of complement of E. So 1 minus 0.168, that gives us this 0.832 or 83.2%. Okay, let's consider two events, E1 and E2, both from the same sample space S. And so we have that the probability of the union of these two events, meaning E1 union E2, is equal to the probability of event E1 plus the probability of event E2 minus the probability of the intersection E1, E2. If this seems familiar, you're not wrong, because this is the principle of inclusion-exclusion. An example. What is the probability of a positive integer selected at random from the set S of positive integers not exceeding 100? And what is the probability for it to be divisible by 2 or 5? Now, event E2, let me call it event E2, is that the integer is divisible by 2. E5 is the event that the integer is divisible by 5. E2 will contain all even numbers, 2, 4, 6, 8, 10, all the way up to 100. And the cardinality of the set is, of course, 50. The probability that E2 happens is then very simply cardinality of E2, 50, divided by the cardinality of the sample space 100, equal to 0.5. Then we have the other event, the event E5, that the number be divisible by 5. This will contain in it outcomes 5, 10, 15, 20, 25, all the way up to 100. The cardinality of this event set is 20. The probability of this event occurring is E5, the cardinality of E5, meaning 20, divided by the cardinality of the sample space, 100, which comes out to 20 over 100, which is 0.2. And then we have the intersection set. The intersection set of E2 and E5 is this one, containing of numbers 20, 30, 10, 20, 30, 40, 50, 60, all the way up to 100. The cardinality of the intersection set of E2 and E5 is 10, which means the probability of the intersection event of E2 and E5 is 10 divided by 100 or 0.1. Now that we have everything, we have the probability of the intersection event, of the individual events, we can find the probability of the union of these two events using the inclusion-exclusion principle. Probability of E2 plus probability of E5 minus the probability of intersection outcomes in the intersection of the two events. And that comes out to 0.5 plus 0.2 minus 0.1 equal to 0.6. Now, what happens if the outcomes of an experiment are not equally likely? In that case, we assign a probability function to each outcome in the sample space S, and two conditions have to be met. First of all, each probability has to be between 0 and 1. Negative values are, of course, not possible, make no sense. The second condition is that all of these probabilities, the probabilities of all possible outcomes added up together, have to add up to nothing other than 1. So each value must be between 0 and 1, and the probabilities must add up to 1, because the outcome is guaranteed to occur. Now, how can we obtain these probabilities P of S? Probability P of S assigned to a specific outcome S equals the limit of number of times S occurs. If you keep running the experiment like a lot of times, divided by the number of times the experiment is performed. Once we know the probabilities, all the probabilities P of S, we can compute the probability of an event like this. You know which outcomes are in an event, just add up the probabilities of those outcomes, and that gives you the probability of said event. So we've got an example over here. This one gets more interesting. Here we have a die that's been tampered with. It's biased. And it's biased in such a way that the number 3 appears twice as often as any other number. What are the probabilities of all the possible outcomes? Now, there are 6 possible outcomes, right? The faces on the die haven't changed, still 6. And instead of drawing those figures, I'll just call those faces S1, S2, S3, S4, S5, and S6. Now, the probabilities of S1, S2, S4, S5, and S6 are all equal, but the probability that S3 shows up is twice the probability of any other face, and we're just using S1 because all the others are all the same. Now, since the probabilities must add up to 1, we have this formula equal to 1. So sum up all the probabilities, it must add up to 1. You got 7 P of S1, move the 7 on the other side, which means that all of these probabilities, S1, S2, S4, S5, and S6, which are equal, they're all 1 by 7. And the probability of S3, you put this in here, the probability of S3 showing up is 2 by 7. Numbers are fine. Sometimes it's nice to see this in PMF form, and this is what this is saying. The probability that 1, 2, 4, 5, or 6 show up is 1 over 7. The probability that we'll see a 3 on this particular die is 2 by 7. Not because it's fair, not because it's normal, but because it's been tampered with. Okay, Let's continue with the biased die, the loaded die from the previous example. What is the probability that an odd number appears when we roll the die? Now, the event that an odd number shows up is an event that contains three outcomes, S1, S3, and S5, 1, 3, and 5. Remember, the probability of an event is equal to the sum of the probabilities of individual outcomes that make up that event. So in our case, that means the probability of an odd number showing up is the sum of probabilities of all numbers that we consider odd, meaning 1, 3, and 5. So just add those up. So you got 1 over 7, 2 over 7 plus 1 over 7, they add up to 4 over 7. 4 over 7 is the answer. You can rewrite that as a percentage if you like, 57.14%. And then we have something called the conditional probability. Now, if you toss a coin 3 times, what is the probability that the number of times you see the tails side, the tails face of the coin? If the first toss is it, if the first, okay, so let me repeat that. What is the probability that an odd number of tails appears if the first toss is a tail already? So kind of have two events here. Odd number of tails appear, and then we have a condition, something that's already happened. If the first toss is a tail. So if the first toss is a tail, the possible sequences are TTH, TTH. First one also always has to be a T, right? THT and THH. Now, in how many of these is the number of tails an odd number? This one, 3. Not this one, because it's 2. Not this one, it's 2. And this one, 1. 1 and 3, so 2. In 2 out of these 4 cases, the number of tails we see is odd. 2 out of 4. Therefore, the probability, because each of these outcomes is equally likely, in 2 out of 4 cases, we see an odd number of tails, given that the first one is already a tail. And so, therefore, the probability of event E happening, given that F has already happened, is 0.5. This kind of probability is called conditional probability, where something random has already happened, and we're talking about events coming after that. If we want to compute the conditional probability of E given F, we use F as the sample space. So for any outcome of E to occur under the condition that F has already occurred, means that outcome must be in E intersection F. So let events E and F be events that have non-zero probabilities. The conditional probability of E given F is denoted like this: P, probability of E, and then we use this half-pipe character, E given F. And that's how we read that, probability of E given F. And its mathematical definition is this equation over here. You find the probability of event E intersecting with event F and divided by the probability of the conditional event, in this case F, whatever's on this side. Should also note that probability of E given F is not the same as probability of F given E. These are not the same things. Okay. What is the probability of a random bit string of length 4 to contain at least 2 consecutive zeros, given that the first bit is already a 0? Okay, so we have one event. Bit string contains at least 2 consecutive zeros. And the other event is F. First bit of the string is a 0. Now, we know the formula for conditional probability is this. That helps us understand what we need. First, let's understand which outcomes are in this intersection event. So, the intersection event that the first bit is already 0 means first bit is already 0. That's all of these outcomes that you see. And there are at least 2 consecutive zeros. This one we have 4, we've got 3, we've got 2, we've got 2, and we've got 2 over here. So we have the intersection event. Let's find the probability of this event. And there are E intersection F, total sample space. We have 4 bits, which means we have 2 to the power 4, 16 possible outcomes in the complete sample space. So 5, got 5 event outcomes over here, so 5 over 16. Then we have probability of F, that the probability that the first bit of the string is 0, that is half. Out of all 16 possible bit strings that you can make, fully half will begin with a 0 and half will begin with a 1. So this is easy, 1 over 2. And then now that we have these 2 probabilities, we can find the conditional probability, which is probability of E intersection F, 5 over 16, divided by 1 over 2. Do the math a little bit and you come out with 0.625 or 5 over 8. Now, let's go back to the example of tossing a coin 3 times. Does the probability of event E, an odd number of tails happening, depend on the occurrence of the other event F, that the first toss is a tail? In other words, is it the case that probability of E given F is not equal to simply the probability of E? We actually find out that the probability of E given F is 0.5. The probability of E is also, just the event E is also 0.5. Which means it doesn't really matter what you know about what happened before, about event F. This means that events E and F are independent events. Knowledge of F, prior knowledge of event F having happened, does not change our perception of whether the other event E, or with what probability event E will happen. It's 0.5 without any knowledge about event F having happened. It is still 0.5 with knowledge that event F has happened. So information about event F having happened does not change our view of the probability that E will happen. That makes them independent. So, because this is the definition of conditional probability, and for independent events E and F, we know that these two probabilities are equal. This can only happen if this probability that we have in the numerator over here, if that is equal to probability of E times the probability of F. If you do that, you substitute it in here. These will cancel out and you'll end up with probability of E. So probability of E given F is equal to probability of E. This is what, so this is a condition. This is an implication of independence. And of course, if E is independent of F, that also means that F is independent of E. So independence is a symmetrical relationship. Okay, example. Suppose E is the event of rolling an even number with an unbiased die, meaning rolling a 2, a 4, or a 6. F is the event that the resulting number is divisible by 3. Are events E and F independent? So probability that divisible by 3 is 3 or 6. So the probability that E happens is 1 over 2, right? 3 outcomes out of 6 possible ones. The probability of F that the number is divisible by 3, 2 outcomes out of 6, meaning 2 out of 6 or 1 by 3. The intersection, the cardinality of the intersection of these two events is 1. Only 6 is found in both. So, more formal notation. You can just add that over here, and F will contain 3 and 6. So then E intersection F, E intersection F is just the outcome that we see a 6, and the cardinality of that is 1. Only 6 is divisible by both 2 and 3. And the probability of E intersection F is then, of course, 1 over 6. Now, is probability of E intersection F, is that equal to probability E times the probability of F? Yes. This 1 over 2 times 1 over 3, 1 over 6. This is also 1 over 6. So, yes, E and F are independent.